Section 5.3, graphs of rational functions in the form f of x is equal to ax plus b over cx plus d. By the end of this lesson, you should be able to determine the locations of the vertical and horizontal asymptotes by examining just the equation of a function. Use end behavior to determine the location of horizontal asymptotes. Use the sign table to determine positive and negative intervals of the function. And then graph the functions when the numerator and denominator have a common binomial factor. The graphs of most functions in the form f of x is equal to ax plus b over cx plus d have two asymptotes. They have a vertical asymptote and a horizontal asymptote. The graph may or may not cross the x-axis, therefore it may or may not have a zero. There are no oblique asymptotes in this case because the numerator and denominator have the same degree. Just recall that oblique or slant asymptotes, they happen when the numerator of the function has 1 degree higher than the denominator of the function. So what we're going to do is we're going to start by looking at this form right here and thinking about vertical asymptotes. A vertical asymptote will occur when the denominator is 0, right? So cx plus d, the denominator here, cx plus d is equal to 0. So when we want to find a vertical asymptote and we have the function in this form, we can just actually use algebra, rearrange this, right? So we can just take cx plus d. We know that that will equal to 0 for the vertical asymptote. The denominator there will equal to 0. So then we'll just rearrange it. And if you want, I can show you how we're rearranging it right here. So we basically do, okay, so cx plus d will equal to 0 in the denominator for our vertical asymptote. Then we do cx is equal to negative d, and then x is equal to negative d over c. And that's what we have right here. Okay. So when we want to find the vertical asymptote of the function, we set cx plus d equal to 0, and we solve for x. Finding the zeros, the x-intercepts, well, because this is a fraction, and this is something that I've said a number of times this unit, a fraction can only be equal to 0 if the numerator is equal to 0. So the zeros, or the x-intercepts, will only occur when the numerator ax plus b is equal to 0. So again, we arrange this right here to find out like what are the x values that will make the numerator 0. So we write ax plus b is equal to 0. Ax is equal to negative b. We bring the b over. And so x is equal to negative b over a. And you may have noticed already that this is incorrect. That was a copy and paste error. That should be negative b over a. Finding the horizontal asymptote. So this has been covered in the previous lesson. You look at the end behavior of the function. As x gets very large and positive, or very large and negative, adding the b in the numerator and adding the d in the denominator becomes negligible. Like, for example, right, if b and d are relatively small numbers, then like if we chose, say, 1,000,000 for x, well, 1,000,000 plus, say, for example, 2, or 1,000,000 minus 2, the plus or minus 2 there is not significant. So as x gets exceedingly large, we just look at ax over cx, right? We take out the b and the d because they're, as it says right here, negligible. So the location of the horizontal asymptote is just basically your ratio of a over c. So the horizontal asymptote there is a over c. Finding the y-intercept. To find the y-intercept, you set x is equal to 0 and you solve for f at 0, right? And that's something that we've been doing now for a while, and you've actually been doing that since grade 9 when you had to find the y-intercept of a line. Once all that information is gathered, it becomes very easy to graph the function. There are 3 cases of the f at x is equal to ax plus b over cx plus d. We can have a case right here where we have an a value, a b value, a c value, and a d value, and nothing cancels, right? So as we can see here, we have a vertical asymptote at 1/2, right? Because if x is 1/2, then we get the denominator equal to 0, which is undefined quantity, and so that's our vertical asymptote. Notice that the y, or the horizontal asymptote right there, is equal to 2 because it's the ratio of a to c, right? If we set the numerator equal to 0, we would find that the x-intercept, which is not labeled here, but the x-intercept is actually 1 over 4. And the next case is like 0x plus b over cx plus d, so where you have a constant in the numerator. Then you have this form where the horizontal asymptote is at y is equal to 0. And the reason why the horizontal asymptote is at y is equal to 0 is because the numerator is a constant value. And if it's a constant value, then that function can never get to 0, because remember, a fraction can only be 0 if the numerator is 0. And so therefore, if it's a constant value, it can never equal 0. So it'll get close to 0, but never equal to 0. And the last one is just f of x is equal to b, some sort of common factor. And that arises when you have, say, if you look right here, 4x minus 8. Well, if you factored out the 4, then you get x minus 2 over x minus 2, which then cancels. So, you know, we'll just do that quickly over here so you can see it a little better. So f of x is equal to 4x minus 8 over x minus 2. And again, you have to, stipulate x cannot equal to 2. Right, so you have already you have a restriction there, but then when we go to factor, we factor out a 4 and we get x minus 2 over x minus 2, and so that will cancel. Sorry, I forgot the closing bracket there. Okay, so then we cancel these, and then we just end up with 4, right? So f of x is equal to 4. F of x is equal to 4. That's just a horizontal line at 4. Right? But we also have this restriction that x cannot be equal to 2, because in the original function that we graphed, or that we had x minus 2 in the denominator. So as you can see here, we have a hole at x is equal to 2 because that was a restriction in the original function. So we're going to get onto actually going and graphing these and going through all the various steps. So it says graph the function f of x is equal to x minus 2, give the equations of the asymptotes, state the domain, range, state the zeros, provide the positive and negative intervals. Always check if there is a common binomial factor first. So what we mean by common binomial factor is there a factor in the numerator or the denominator that we can cancel, right? Like in the previous example, that we just did here, the common binomial factor in the numerator and the denominator was x minus 2, and we canceled that out. Well, if we take a look at this function, there is no common binomial factor there, right? Like we have x minus 2 in the numerator, but there is no way that the denominator has x minus 2. So we do not have case 3, right? If we look at this, to me, this looks the most like case 1, right? Where I have ax plus b, cx plus d, right? So if you want, you can even actually say, all right, well, I know what a, b, c, and d are, right? So you can just actually put them up here. So if I write here, f of x is equal to x minus 2 over 2x plus 3, right? I can actually write out that a is equal to 1, b is equal to negative 2, c is equal to 2, and d is equal to 3. So recall that if I want to find the equation of the asymptote, right, the vertical asymptote, it's negative d over c, right, because I'm finding the x value that will cause the denominator to be equal to 0. So what I'll do right here is I'll say vertical asymptote. And that's equal to negative d over c. So the vertical asymptote is, sorry, I should write x is equal to, let me just clean that up a little bit. And we're back and it's cleaned up. So we go x is equal to negative 3 over 2, right? Now you don't actually have to write this equation and sub in the values. If you just look at the denominator and you're able to ascertain the vertical asymptote, that's fine. You can totally do that. Okay, now the horizontal asymptote, recall that we have to look at the end behavior. So as the function goes to infinity, what is the ratio of a to c, right? So y is equal to a over c. And so therefore the horizontal asymptote in this case, well, my a value is 1 and my c value is 2. So I've got a horizontal asymptote at 1 over 2. I'm going to take a look at now, let's see if there's any zeros. Well, remember this is a fraction. So if it's a fraction, that means that the numerator has to be 0 if the fraction is equal to 0, right? So I'm going to put x-intercept right here. And my x-intercept is given, as you've seen up here. Sorry, just scroll up here for you. X-intercept is negative b over a. So x is equal to negative b over a. And so x in this case is equal to 2 over 1, right? So negative, and b was negative 2. Right, so x is equal to negative 2 is just 2 over 1 is just 2. So my x-intercept for this graph is going to be 2 and 0. Okay, so I can plot that right here. Okay. All right, and then I'm going to look at my y-intercept. Okay, and so my y-intercept is I set the function equal to 0. Yes, so I set the x value equal to 0. That's what I meant. Set x equal to 0. Well, if x is equal to 0, then my y-intercept, if I go back to the original function, if x is equal to 0, well, 0 minus 2 over 0 plus 3, that's negative 2 over 3, right? So f at 0 is equal to 0 minus 2 over 2 times 0 plus 3. So my y-intercept is negative 2 over 3. So it's down here. Negative 2 over 3 should be right here. Okay, plot that point right there. Okay, so now I have the vertical asymptote, I've got the horizontal asymptote, I've got my x-intercept, and I've got my y-intercept. And so what I'm going to do is I'm going to start by plotting the asymptotes, and then I'll take a look if I can plot anything else. So when I come back, the asymptotes will have been plotted. The last thing that I'm going to do is I need to know how to draw this function. Like, am I going to draw it up here and down here, or is it going to be in this quadrant, like for example in the second quadrant and the fourth quadrant, or is it going to be predominantly in the third quadrant and the first quadrant? Well, I can see that these 2 points are here already, so that tells me that my function is going to be in the second quadrant and in the fourth quadrant right here, because I already have 2 points in the fourth quadrant, right? So I know that it's probably going to be in this quadrant. But what we can do though is we can look at the behavior around the vertical asymptote, right? So if I say I'm going to do basically a table of value, or sorry, an interval table here. And so I'll do my interval table right here. I'll do so x less than the vertical asymptote at negative 3 over 2, and x greater than negative 3 over 2. Okay. And what I find is that if I take a look at my function, so I look at the different factors, x minus 2, 2x plus 3, and then my overall positive or negative. So I'm going to take a value here of x less than negative 3 over 2. So I'll say, like, let's say negative 2. So negative 2 minus 2, that's going to be negative. And then negative 2 times 2 is negative 4. Negative 4 plus 3 is equal to negative. So therefore, when I have this factor, as you can see right here, I've got x minus 2 divided by 2x plus 3. So x minus 2 divided by 2x plus 3. So negative divided by a negative gives me a positive. Okay, so I need to have positive values of the function to the left of my vertical asymptote. So that means my function's got to exist in this portion of the graph. And then if I take, for example, values greater than -3/2, we have to be careful here because, for example, if I took -1, well, I would still end up, I'd end up with negative values, right? And so I would end up basically in this quadrant here, right? So you would still have, you'd still get the shape that you're looking for, right? So for example, if I chose -1, -1 minus 2 is -3, so that's a negative. -1 times 2 plus 3 is -2 plus 3, so that's equal to positive. So my function is going to be negative on that interval. So it works out that we see, okay, so that means that this is how I'm going to have to draw my graph, something like this. Oop, that was horrible. I'm going to try that again. Okay, so that's a little better, but just hard to draw with the stylus. Okay, so the interval table here, by taking test values to the left and to the right of the vertical asymptote, can often help us, in addition to having both the x-intercept and the y-intercept, know which way this has got to be plotted. So then I'm going to have to say, okay, so give the equations of the asymptotes. So I have the equation of the vertical asymptote, that's right here. I've labeled that already. And the equation of the horizontal asymptote is right there. And then I'm going to have to state the domain and range. So domain is x element of all real numbers such that x cannot be equal to -3/2. And the range is y element of all real numbers such that y cannot be equal to 1/2. State the zeros. So I have my x-intercept already. I wrote that down as 2, 0. And the positive and negative intervals. Okay, so the positive intervals right here, so I'll write my positive interval. If I look at the graph is positive, right, from x element of -infinity all the way up to, but not including, -3/2. And then the graph becomes positive again after the x-intercept. So I have to say here and then 2 and positive infinity. And so the negative interval, therefore, is just in between. Right? This is where the function is negative right here. So then between -3/2 and 2, that's my negative interval. Okay, so I think I've done everything that the question has asked us to do. I've got the domain, range, state the zeros, provide the positive and negative intervals, and then just checked everything over, and this looks good. Okay, I'm going to move a little bit more quickly through this example. This example states that the graph of the function is 3 over x minus 2. So if I take a look at that, which case is that? Well, that's case number 2. Right, b over cx plus d, and recall that because I have a constant in the numerator cannot be equal to 0. So I already know that my horizontal asymptote is going to be y is equal to 0, right? So because this fraction here could never equal 0, because the numerator can never equal 0. 3 can never be equal to 0. So okay, so I'm just going to rewrite my function here, and I'm just going to do this by inspection. My vertical asymptote is x is equal to 2, because if x is equal to 2, then the denominator is equal to 0. My horizontal asymptote is y is equal to 0. We've talked about that already. And then we have to basically look and see if we can find the x-intercept. So I want you to think about that x-intercept, for example, which is the next thing that we have to do, right? The x-intercept, which is negative b over a. So maybe you thought about this and you're like, okay, well, negative b, if I look at this, that means that I have x is equal to negative 3 over, and my a value here is 0 because a is, ax plus b. Oh, wait a minute. I've got negative 3 over 0. Well, x-intercept then does not exist, right? And that makes sense because if I have a horizontal asymptote at y is equal to 0, that means my function will never cross the x-axis. So I do not have a x-intercept. Let's look at a y-intercept. Okay, now just take a look at the function right here and see if you can set x to 0 and see if you can figure out where the y-intercept is going to be. Okay, so when we set x to equal to 0, my y-intercept is 0, negative 3 over 2. So that means that my y-intercept is somewhere down here. Okay, negative 1/2. Okay, the next thing that we're going to do is I'm going to plot my vertical asymptote and my horizontal asymptote. Okay, by plotting my vertical and horizontal asymptote, and I see that my my y-intercept is located right here. I think I can now know that this graph, I don't even have to do my positive and my interval table before and after the the vertical asymptote. Because I have this point down here, I know which way that this function is going to behave. We're going to basically trace down here, and then we're going to go opposite and trace over here. Okay, so in this case, I'm not going to do a interval table because it's not necessary. Okay, so there's my function, just approximately sketched. So, oops, sorry, I apologize. It's this one right here. I was on the wrong one. That's my function approximately sketched. So let's we have the equations of the vertical and horizontal asymptote already. I've listed them right here. The next thing is to state the domain and range. Okay, so domain is x element of all real numbers such that x cannot be equal to 2. And range is y element of all real numbers such that y cannot be equal to 0. I have no x-intercept. I have no zeros. Positive and negative intervals. Sure, so this is the positive interval is going to be x element of 2 to infinity, right? So it's positive right here. And then the negative interval is x element of negative infinity to 2. Okay, the last example about graphing is fairly straightforward, and that's because it is an example of the third case, and I'll show you why that is. So f of x is equal to negative 2x plus 2 over x minus 1. And so I see right immediately that x cannot equal to 1, right? So, but when I go to factor the numerator, I see that there is a common binomial factor here. So those cancel. And then I have f at x is equal to negative 2, but I have to stipulate that x cannot be equal to 1, right? So I'm going to draw a horizontal line at negative 2, but I will have a hole at x is equal to 1. So that will be a hole there, okay? So there's not much else that you really have to do here. You just have to draw a straight line through x minus 2 and then indicate that there is a hole at that value. Okay, so I've drawn this right here, and one of the things that I have there is I have that open circle over here. Now, just because I was doing this in Word, I wasn't able to break up the line. You should not be drawing a line through the open circle. That should just be an open circle right there. And so one thing we still need to do, like the equations of asymptotes, we don't have any asymptotes. Domain and range. Domain is x is an element of all real numbers, but x cannot be equal to 1. Okay, and range is y element, so y is actually just equal to -2. Okay, because there's no other value that y achieves. State the zeros. Well, we've got no zeros. Provide positive, negative intervals. We have no positive intervals, so all we have is a negative interval, and that is x element of -infinity to positive infinity, right? Because it's always a negative function. So that one was a fairly straightforward one, and that's a result of it having that common binomial factor that we can cancel. Okay, write equation of a function that has a horizontal asymptote at y is equal to 2 over 5, a 0 at -3 over 2, and a vertical asymptote at x is equal to 2 over 5. Okay, so remember that this is our general form of our function. F at x is equal to ax plus b, cx plus d, right? So if I have a 0, and remember that your x-intercept is given by the function x is equal to -b over c, right? So if my 0 is -3 over 2, so then x is -3 over 2 is equal to -b over c. Therefore, b is equal to 3 and c is equal to 2, right? That negatives cancel. And so I have, sorry, -b over a is your x-intercept. I'm sorry, that was a silly mistake. I keep making that. Okay, sorry, and your horizontal asymptote, right? We have the horizontal asymptote is y is equal to 2 over 5. Well, we know that the y asymptote has the equation y is equal to a over c. Okay, I already know that I've got the equation, so 2 over 5 is equal to a over c. Therefore, I know a was already 2 because I had it down there. Therefore, 5 is equal to c, right? Okay, I've got a, b, and c. Now to just find d, and d is given by the vertical asymptote, right? So the x asymptote is given by the equation x is equal to -d over c, and so I have there 2 over 5 is equal to -d over c. So therefore d, right, if I multiply both sides by -1 times -1 times -1, that would cancel the negative. And so then I would have -2 over 5 is equal to d over c. Well, I already know that 5 is equal to c, so therefore d is equal to -2. And then I can just write in my function, right? So therefore f of x, ax plus b, so my a was 2, 2x plus 3, all over 5x minus 2. And there's the equation of the function. Final example, write the equation of the function that has a horizontal asymptote at y is equal to 0 and a vertical asymptote at x is equal to -3 and is always increasing. So again, I'm just going to say like f of x is equal to ax plus b over cx plus d. Okay, so the first thing that I have is I have the horizontal asymptote, and so therefore y is equal to a over c. That's the equation of the horizontal asymptote. I know that 0 is equal to a over c. Well, if that's a fraction, right, a fraction can only be 0 if a is equal to 0. So a is equal to 0. All right, so I've got my a value there. My vertical asymptote is given by the equation x is equal to -d over c. Right, and so therefore -3 is equal to -d over c, right? So that means canceling out the negatives, okay? Therefore I have 3 over 1 is equal to d over c. So that means that therefore d is equal to 3 and c is equal to 1. So when I go to write the equation of my function here, what you'll notice is that I basically have b, some constant value, over x plus 3, right? Okay, so just to make this easy on myself, I'm going to see if b is equal to 1, then I would have f of x is equal to 1 over x plus 3. That to you should signify, right? So this is what you should do. You should be thinking about this in your head. Well, 1 over x plus 3, that's just the reciprocal parent function, right? That's the reciprocal parent function shifted to the left 3 units, right? So that means, okay, that's my reciprocal parent function just shifted over to the left 3 units, right? That's what that is right there. Right, so this is your parent reciprocal function, 1 over x, and then because there is a horizontal translation 3 units to the left, that's what I would have. However, take a look. It says that this has to be always increasing. And if we look at this function is strictly decreasing. So what would I have to do to be able to get this to be strictly increasing? Well, if you said that you have to reflect it in the x-axis, you'd be right. So I have to reflect this in the x-axis so that it is always increasing. So this one does not work. However, f of x equal to negative 1 over x plus 3, because remember, a negative in front of the function means that there's a reflection in the x-axis. That is a function that satisfies all those requirements. Okay, so I chose b equal to 1, and then I plotted this, and it was, again, just the parent function moved over to the left, but then it did not satisfy the requirements that it was always increasing, because the blue function is always decreasing. And so therefore I had to reflect it in the x-axis to provide the correct restriction that it always had to be increasing. So negative 1 over x plus 3. Okay, great. There's your homework, and thanks for watching.